We present our paper where we show the potential of exploiting vertex-centric parallelism to compute SQL join queries. One way to speed up join processing is to take advantage of parallelism. In particular, we focus on exploiting what's called a data parallelism, that is, executing a join operation in parallel on multiple parts of the input. As this example here demonstrates, we have two relations, R and S, that are horizontally partitioned based on their bjoin attribute values. Each value is assigned to a processor. And once the input is distributed, processors can compute the join in parallel, independently of each other. This, however, requires to reshuffle the input based on join attributes between individual join operations. This technique of horizontally partitioning the input to parallelize the join computations has been adopted by the following classes of systems. So here we have examples of early parallel databases from the 80s, as well as the ones that are known and used today. Then there is a class of systems referred to as big data systems that have been developed for general purpose computations and not specific to SQL workloads, however used a lot for join processing. Our work uncovers the potential of graph processing engines to evaluate SQL queries. There has been no prior work that extensively studied evaluating SQL on top of native graph backends, both theoretically and practically. And in particular, we focus on graph systems that employ vertex-centric computational model. The input to the computational model is a graph. And graph, as we know, is a collection of vertices and edges that can each store data. And so the vertex-centric computational model is an adaptation of bulk synchronous parallel model to graph data, where each vertex plays a role of a processor that performs a computation on its local data and communicates with other vertices. So our computation proceeds in super steps, and we start by activating vertices. Active vertex is shown in green here, and I'm just using one vertex for simplicity. At each super step, each active vertex starts by executing a user-defined program on its local data, and then can send messages via either outgoing edges or directly to a vertex whose ID is known. Then there is a synchronization barrier where vertices wait for the messages to be delivered. And then we start the next super step, and vertices that receive the messages are now active and continue the computation. The great advantage of this model is its inherent parallelism, in the way that all vertices can do computation in parallel independently of each other. We estimate the cost of a vertex-centric algorithm using the total communication and computation costs. The communication cost measures the total number of messages sent by vertices over all super steps. We account for computation costs to make sure that when designing algorithms, vertices perform limited work, which doesn't exceed the communication cost. We also want to make sure that the number of rounds is linear in the size of the query, which we assume to be constant, since we're interested in data complexity of an algorithm. In our paper, we present the solution to show that vertex-centric parallelism is extremely well suited to compute SQL queries with provable theoretical guarantees and good performance, as validated by our experiments. There are two main parts to our vertex-centric solution. It's a graph encoding of a relational database instance, which we call tuple attribute graph data model, TAG for short, and tag join algorithm, specified as a vertex-centric program running over tag inputs. Tag join is competitive with the best-known parallel join algorithms and avoids the need to rehash or to resort the input between individual join operations. We begin with the tag data model, which I'm going to explain using this example of relational database instance. Let's start with the donation table. Each tuple of a relation maps to a vertex, which we refer to as a tuple vertex. So we take the first tuple and create tuple vertex nation 1. Then each attribute of a tuple also maps to a vertex, which we call attribute vertices. So we distinguish two classes of vertices, attribute and tuple. We use different shapes to distinguish them just for the clarity reasons, but all vertices have the same functionality in the vertex-centric computational model. If an attribute value belongs to a tuple, we connect the corresponding vertices to their tuple vertex, where the edge label corresponds to the name of the attribute. Let's continue with the next relation, customer, and take the first tuple and map it to tuple vertex. Then each attribute value of this tuple maps to an attribute vertex. Then we add edges to connect attribute vertices to the tuple they belong to. As you can see, we don't duplicate attribute vertices. If a value exists, then just add an edge with appropriate label. We apply the same steps for each tuple of each relation in the database, and this is the resulting tag instance that we obtain. It's query independent, therefore can be computed offline, and the size of the graph is linear in the size of the relational database. The most prominent feature of the tag data model is that it naturally captures join relationships. As in, tuples that join are explicitly connected via edges to the attribute vertex value that they share, which means that we are not limited to primary foreign key joins compared to existing encodings, but that we can join relations based on the equality of any attributes. In addition, attribute vertices provide us an implicit indexing scheme, as in from an attribute value, we can quickly navigate to tuple vertices that contain that value by simply following the outgoing edges. The tag encoding, in combination with the underlying vertex-centric computational model, makes it easy to check the join conditions in parallel. Let's consider a two-way join example. Here we have tag encodings of relations R and S. We start the computation by activating attribute vertices that correspond to join attribute B. Active vertices are shown in green, and so each active vertex checks if it can serve as a join value, as in it has edges of both types, R and S. If yes, then vertex sends the messages via those edges to tuple vertices. Activated tuple vertices send their values back to the attribute vertex, which then combines the received values to construct output tuples. If you notice, B1 vertex is performing a Cartesian product of received A and C values. The advantage of vertex-centric computation is that we don't need to partition the input relations based on the join attributes, which makes it different from the existing parallel join approaches. Let's analyze the cost of the two-way join algorithm. So super steps 1 and 2 have the same cost, so similar analysis applies. In the computation phase, each B vertex checks its outgoing edges, and we know that the number of outgoing edges is at most the number of tuples in the input. Similarly, in the communication phase, join vertex B sends messages along its outgoing edges, and again, number of messages is at most the size of the input. However, if we look closer, we can refine the communication cost here, since B only sends messages along edges when it knows that it's a join value. For example, B2 and B3 vertices do not send any messages. So the communication cost is actually upper bounded by the minimum of input and output sizes, which becomes important when the size of the output is much less than the input. In super step 3, computation is basically going to be exactly the size of the output, since we're only doing a Cartesian product of values that qualify to be in the output. And assuming that the join results are sent to a centralized location, communication is also linear in the size of the output. We can improve the cost of super step 3 if we consider a more compact representation of the output. In the worst case, we can have such instances of RNS that all tuples join, and the size of the output will be n squared. But with the more compact factorized representation, we can reduce the size of the input to be just in. Building it requires less computation, and it incurs less communication to transmit factorized output in this example. And here is the updated analysis of super step 3, where we take into account the factorization. We state our first result by saying that any two-way join can be computed in a vertex-centric way with the cost linear to the input plus output size. And with an observation that the join result can be factorized, we can obtain the total cost that is linear in the input size only. We continue by extending a two-way join algorithm to multi-way cyclic queries. The acyclic join algorithm is a vertex program that is executed in parallel by all active vertices. It consists of two phases. In the reduction phase, we essentially perform a vertex-centric analogy to a semi-join reduction technique. And so we mark edges that connect vertices that contribute to the join output. The collection phase then traverses the marked subgraph corresponding to a full reduced input to collect the actual join result. The input to the algorithm is a tag plan that describes the graph traversal, and so it drives the vertex-centric program so that each active vertex knows along which outgoing edges to send the messages. We use generalized hyper-tree decomposition of the join query as a basis to obtain a tag traversal plan. Let's look at it through example. We have an acyclic query whose generalized hyper-tree decomposition is a join tree shown on the left, and by following steps that are detailed in the paper, we construct a tag plan. Here it's color-coded to show the correspondence between the join tree nodes and the tag plan nodes. The resulting tag plan describes the traversal steps, where each step maps to a superstep of a vertex-centric computational model. First, we'll start with the bottom-up reduction and go up towards the root. In this case, let's establish blue vertex as a root. Active vertices check join conditions, where each vertex iterates over its outgoing edges and checks if it has the appropriate edge labels as given in the join conditions. If yes, then a vertex sends a message along that edge and marks it as a potential candidate for the output. The bottom-up traversal only reduces the root relation. So in order to reflect the effect of the reduction on other relations and to fully reduce the input tag representation, we go top-down, and we only follow the edges that were marked during the bottom-up traversal. Then we go into the collection phase. And in bottom-up traversal, collect the output tuples. Marked edges guide the collection phase, and that's how we end up only visiting the vertices of the reduced subgraph. Let's illustrate the algorithm execution using this example of a tag instance. We start by activating cJoin attribute vertices that check the corresponding join condition, and if it's satisfied, mark the edges shown as dashed lines and send a message along those edges in the bottom-up order. Now activated tuple vertices propagate the messages further in the bottom-up order and mark the edges along the way. Join attribute vertices again check the join condition and send the messages only if it's satisfied. Now we go top-down in the reduction phase, following the dashed edges only. Remember that dashed edges were marked during the bottom-up traversal. And as we go top-down, we mark edges with bold, confirming that they are on the join output path. You can see that after the reduction phase, the bold edges signify the reduced subgraph that corresponds to the join output. So we start the collection phase and just follow the bold edges to collect. Attribute vertices combine the received tuples well to construct intermediate results and propagate them further as messages. Double vertices append their values to the received intermediate result and send it further along the marked edges. And we're done. The result is distributed among blue vertices, which can stream the output to a centralized location. With this, we obtain our next result and claim that we can compute any acyclic join query in a vertex-centric way with communication and computation costs that is linear in the size of the input plus output. The detailed cost analysis can be found in the paper. So our algorithm is a vertex-centric analog of Yanakakis' algorithm with the advantage of being naturally parallel. This table demonstrates how our acyclic vertex-centric join algorithm compares against the best parallel join algorithms. So here we have hash-based parallel join and a parallel sort join. Both rely on resorting or rehashing the input based on join attributes, which impairs the applicability for ad hoc queries with different join attributes, and also to the scenarios when data is not read-only. We then extend our algorithm to arbitrary cyclic joins and begin with a triangle query, the simplest cycle. Our worst-case optimal vertex-centric algorithm is competitive with existing approaches in a centralized setting, as well as a distributed setting. In addition, our parallel triangle algorithm doesn't rely on any additional index structures based on global attribute order to achieve the worst-case optimal guarantees. We then generalize triangle query algorithm to compute n-way cycles in a vertex-centric way. So in summary, we solve the following classes of queries. These algorithms are then serve as key ingredients to obtain the complete tag join algorithm to evaluate arbitrary equijoin queries. Our tag join algorithm is broadly inspired by GEM, which is a generalized version of parallel Yanakakis for arbitrary join queries. We also extend our results beyond joins to show that tag join approach is compatible with the efficient evaluation of other SQL operations, such as selection, projection, aggregation, including nested subqueries. Now that we have built the theoretical foundation, we show the practical feasibility of the vertex-centric parallel computations. Our solution applies to both intra-server and distributed cluster parallelism. So we conducted experiments in two settings. In a single server setting, we compare tag implementation against open source and leading commercial relational databases, as well as against Spark SQL. Tag is implemented using TigerGraph, a graph database that supports vertex-centric style computations and is built on top of native graph storage. We used TPCH and TPCDS queries in our experiments. These are standard database benchmarks that relational databases are traditionally tuned for. In total, we have implemented a little over 100 SQL queries of various complexities. These are aggregate runtimes of TPCH queries, shown at scale factor 75. And as we can see, tag join outperforms Postgres and Spark SQL, while being competitive with the commercial databases X and Y. Results for TPCDS queries demonstrate that tag join is particularly well suited to data warehousing scenarios, where we have Snowflake schemas with primary foreign key joins. In aggregate, tag join outperforms all relational systems by at least 4x. We also conducted a preliminary distributed setting experiments using a cluster of 6 machines. Here we compare tag implementation on TigerGraph against Spark SQL using the same set of queries. Here are the results of aggregate runtimes. On TPCH, we outperform Spark SQL by 2x and show a quite competitive performance on TPCDS queries. We also measured the total network traffic, and as you can see, on TigerGraph incurs a lot less traffic than Spark SQL on both TPCH and TPCDS queries, since with tag join we avoid shuffling and broadcasting of relations that Spark SQL does. And so in summary, in this paper we have shown the potential of vertex-centric parallelism to evaluate SQL queries. On the theoretical front, we have parallel algorithms with optimal communication and computation complexities. And on the practical front, we proved to be competitive with the leading relational engines on TPC benchmarks in both single server and cluster settings. For details, please refer to our paper, as well as the extended version published on arXiv. Thank you.